All right, for the sake of time, I think we'll get underway here today. So thank you all for joining us today for the second webinar course being offered by the planning sector as part of the Manitoba Climate Resilience Training Program. The MCRT project has been generously funded by the Government of Manitoba, as well as Natural Resources Canada as part of the BRACE program. The Prairie Climate Centre is very excited to present today's webinar, Manitoba's Changing Climate. The PCC is a not-for-profit organization that is committed to communicating the science of climate change to all Canadians through narrative filmmaking, research reports, community outreach, and what we'll explore in depth today, interactive visualization platforms. My name is Stephen Muirhead, and I'm a research associate with the PCC. We're also very fortunate today to be joined by Matthew Loxley, also a research associate, and once again, Dr. Danny Blair, co-director of the PCC. So thank you both for joining us today. Prior to starting the presentation, I'd like to take a moment to acknowledge that we are gathered today in Treaty 1 territory, within the traditional territories of the Anishinaabe, Inana'eo, Oji Cree, and Dakota peoples, and in the homeland of the Métis Nation. So as an overview for today's presentation, I'll start by introducing some general climate change projections for Manitoba and review recent extreme weather events before handing it off to Matt to provide a tour of the Climate Atlas of Canada. Following the live demonstration, Danny and myself will discuss how specific climate variables and their projections align with observed data. So the first question to answer is, why is there a dedicated course on climate change for the impacts faced in Manitoba? For professionals and decision makers working in Manitoban communities, it's important to understand how to employ climate projections in decisions being made today, and subsequently, what types of responses are required for tomorrow. In the course of today's presentation, we won't necessarily get into exact responses. Those will be tackled in future courses being offered in the individual sectors, but we'll highlight some of the concerns going forward as we've identified them. As mentioned in our first session, Climate Change 101 about a month ago, the prairies in northern Canada are warming at an accelerated rate compared to the rest of the nation. While this project largely focuses on adaptation, it bears reiterating how the two main responses to climate change differ. So as defined by the IPCC, adaptation is the process of adjustment to actual or expected climate and its effects in order to moderate harm, maintain services, and or exploit beneficial opportunities. In short, adaptation is anticipatory. Mitigation, in this case of climate change, is the use of human interventions to reduce emissions or enhance the sinks for greenhouse gases. Mitigation efforts are largely reactive and attempt to contend with conditions as they currently are. So how is climate change going to present in Manitoba, and how will those impacts differ throughout the province? While we often self-identify as a prairie province, that ecozone only accounts for roughly 11% of our total land area. And communities in the north of the province will experience climate change impacts quite differently from those of us in the south. To borrow a line from Jeff Frank, who's a practicing landscape architect, or rather was a practicing landscape architect in the province, Manitoba's projected future is going to be one that is hotter, drier, wetter, and weirder. Another way of thinking that statement is that as we move forward, we're forfeiting the norms as it relates to predictable climate patterns we've used to make predictions about infrastructure, as well as planning. So how that shift is going to be experienced will be in two very different ways. Slow onset events, or what is sometimes referred to as compounding events, and extreme weather events or catastrophic ones. And I've included here as well just a brief description for slow onset that's provided in the Cancun Agreement. So while the impacts of slow onset events may take years, if not decades, to present and become noticeable, extreme weather events are almost always immediate and very self-evident. Manitoba has historically been noted for its climatic variability, and the occasional intense storm or spring flooding event are not new phenomena for us. That being said, the cost of natural disasters are increasing. Since 1983, 13 of the 20 costliest natural disasters in Canada have occurred in the prairies, usually in the form of overland flooding or wildfires, and in some instances, out-of-season storms. With or without climate change, extreme weather events and natural disasters will continue to persist. The concern is that some climate change impacts may contribute to the factors that feed into those events. So when we discuss extreme weather, it's important to parse out what can be directly attributed to climate change and what cannot. Attribution is the process of evaluating the relative contributions of multiple causal factors to a change or event with an assessment of confidence. So we'll now take a look at some examples of extreme weather in province and the associated impacts of notable events, bearing in mind that we aren't directly attributing climate change to those events, but rather focusing on their magnitude and their cost. So droughts have historically occurred in the prairies with some consistency, and that isn't going to change. But with warmer summer temperatures and greater precipitation variability projected for the region, the frequency and the magnitude of drought events may increase in the coming decades, according to some studies. A few significant droughts and associated figures from recent years. So 1999 to 2004 saw Canada's GDP shrink due to drought, with the fiscal year 2001-2002 registering a $4.5 billion loss alone as a result of that drought. 2017 was the driest summer recorded since 1978, or in a 70-year period. And more recently, this past summer saw Manitoba experience some level of drought on all its agricultural land, or about 43% of the province's land area was in a state of drought in 2021. In the same vein, wildfire risk also increases in drought-stricken years for the same reason. The conditions are drier and they're hotter. This past fire season was the fourth worst one in the last century in terms of area burned. It is also one of the longest fire seasons recorded, with the first outbreak starting in late March, and the last few fires declared extinguished in early October. Over recent decades, the length of the fire season has been steadily increasing, and by some estimates, it is now 3 weeks longer than it was in the mid-1950s. Now, for Manitobans, flooding is synonymous with the change in seasons from winter to spring. I'd wager everyone in attendance here either knows someone who has been directly affected by flooding or else has experienced evacuations themselves. I know I myself was evacuated in '97 as I grew up in St. Norbert. So the factors that lead to flood events are numerous and complicated, and as such, attributing climate change directly to flooding is a misnomer. 1997 saw over 25,000 individuals evacuated and 1,000 homes damaged, largely outside of the floodway. In response to '97, though, upgrades to the floodway now allow for protection up to a 1 in 700 year event, which is a great example of an adaptation response, which circumvented over $10 billion of damages during the 2009 flood on the Red River. Since 1968, the floodway has prevented more than $40 billion in flood damage in Winnipeg, but at times that has occurred to the detriment of communities that fall outside of that boundary. And more recently then, near back-to-back floods on the Assiniboine in 2011 and 2014 highlighted the need for the province to adopt a 1 in 200 year flood standard, which it subsequently did, and that was up from a 1 in 100 year standard for planning-based decisions and infrastructure. In 2014, the damages from that flood accounted for about $1 billion in Brandon and along the Assiniboine flood basin. The last extreme weather event I wanted to quickly touch upon is one that I'm biased towards, coming from an arborist and landscape architecture background, but it equally serves as a reminder for communities of the short-term economic costs of extreme weather events and out-of-season storms. The Thanksgiving storm of 2019 saw extreme gusts, an excessive amount of heavy, wet precipitation fall in the span of 4 days, resulting in about $10 million cleanup tab for the city of Winnipeg. In terms of improving the resilience of Manitoba communities, accounting for more maintenance and replacement costs in annual budgets is one of the many adaptive measures that we should be undertaken and will be explored in future courses amongst various sectors. So as we continue to contend with extreme weather in Manitoba, the government has stated that its mission is to become Canada's cleanest, greenest, and most climate resilient province, as noted in the Climate and Green Plan, released in 2017. Of the 4 pillars they present, it is under the adaptation imperative of the climate pillar where the work of BRACE and sessions such as this are the most applicable: to increase climate knowledge, to improve the resilience of communities, and to promote sustainable agriculture. So at this time, I'm going to hand over to Matt to give us a comprehensive overview of the Climate Atlas of Canada, which is one such tool that empowers people to make informed decisions as we work towards a stated goal of becoming more climate literate and resilient. Matt, take it away.
Great, thanks, Stephen. So one of the tools that we have developed at the Prairie Climate Center is called the Climate Atlas of Canada. It is an online tool that is designed to make climate change more approachable and relatable for people living in Canada by combining climate science, storytelling, data, and mapping in one place. So for this section, I will go through how the atlas was created, followed by a brief demonstration of how to use it. Next slide, please, Stephen. So the creation of the Climate Atlas was made possible through the support and funding of a number of different organizations, including the University of Winnipeg, where the Prairie Climate Center is located, as well as a number of different government bodies. The Climate Atlas is also part of a network of data portals and climate organizations, including the federal portal climatedata.ca. We all provide data from the same source, and we work together to ensure that you have the most up-to-date data and that everything is of quality and consistency across the portals. So the Climate Atlas uses data from 24 different climate models and 2 different carbon emission scenarios, and has then been downscaled to capture the local geographies of Canada. The data was originally obtained from the Pacific Climate Impact Consortium, which is a research center in Victoria, BC. The dataset consists of modeled daily temperature and precipitation data for almost 150 years, from 1950 to 2095, for a 10 kilometer by 10 kilometer grid resolution that covers all of Canada. So we've taken that data set and processed it and analyzed it and turned it into something that is a bit more digestible in terms of an interactive maps and graphs that are found online. So in this way, the Atlas is a useful tool for visualizing what climate change may mean for Canada. And as a result, has been used for climate change adaptation planning and risk assessment processes. But beyond climate data, there are also a number of different content types that can be found online, such as easy to understand explanations of climate science, special topics and articles on key areas such as cities, agriculture, and health, and how they relate to climate change. There are also climate summary reports for major cities and data printouts for other locations. And finally, there are short documentaries that tell stories about climate change across Canada from the local perspective, how people are dealing with the challenges of climate change and what it means to them. So the best way to understand how the tool works is through a quick demonstration. So I will give you a tour and show you how the site works. Stephen, yeah. So this is the homepage of the Climate Atlas. There are many different ways you can navigate to the different content types. The first is by scrolling down through the homepage, where you'll see some of our featured content, such as the basics of climate science and climate change, our special report on heat waves and health, as well as our climate summary reports for major cities across Canada. On the top right, there are also quick links to some of our more common content types, such as our map, our topics page, our inventory of videos, as well as our inventory of articles. On the top left is a menu button, which gives you more specifics about what is available on the site, such as our Find Local Data page, which I'll explore later, as well as our Downloads page, where you can download maps and images and other types of content. But for now, I'll take you to the map. So this is our map page. It is an interactive way to see what climate change means for your community. Specifically, it is showing what climate models are projecting the future climate to be in Canada based on different greenhouse gas emission scenarios. The map shows the average of 24 climate models for a given 30-year period for a given climate variable, which both can be adjusted. The bottom buttons and sliders control what map is being displayed at any given time, according to the climate variable, the time period, or the amount of climate change you want to see. At the top is the title that shows you what is being displayed on the map. And to the left is a legend that tells you what the values of the colors are on the map. So for example, if this is your first time visiting the map, you will see a map showing the annual average number of very hot days, or days that reach 30 degrees Celsius or higher, for the high carbon emission scenario or more climate change for the time period 2021 to 2050. And on the map, areas that have a lot of very hot days are shown in red. So you can see down in the prairies here and in Southern Ontario. And for areas of the map that don't have any hot days, they'll be shown more in blue. So you can see the map provides a larger sense of what the models are projecting the future climate in Canada to be, and it allows you to see patterns on a regional scale. However, the map also allows you to see what's happening at the local scale. Every grid square and every place name can be clicked, and it'll provide you specific information about that region or location. So for example, if I click on Winnipeg, a sidebar will pop up, which will show you the value for Winnipeg, the number of 30 degrees Celsius days on average in a year for the time period 2021 to 2050, which is just around 30. It'll also tell you the number on the annual basis for the baseline, which is 1976 to 2005, and how much that has changed. In this way, it is a useful tool for municipalities and regions as they can see how climate change will affect that specific area. To navigate the atlas is similar to how you might navigate Google Maps. You can click and drag to move around the map. You can also use your mouse scroll wheel to zoom in and out. And you'll notice as you zoom in, more and more locations and place names will show up. You can also use the plus and minus buttons on the side to zoom in and out as well. And if you're on your phone, you can use the GPS to find your exact location. When you first arrive on the map, you'll want to decide what sort of climate information you're looking for. So we've taken that precipitation and temperature data and broken it down into indices, or what we call climate variables, that we think are more relatable to people. So we've organized these variables into 5 different categories for easier navigation. These are located at the bottom of the screen. If you click on one of the buttons, a tab will pop up, which will give you a selection of variables to choose from. And every time you click a new variable, the map will change. So there are variables related to hot weather, such as the number of very hot days or tropical nights, which is when the minimum temperature doesn't go below 20 degrees Celsius. There are variables related to cold weather, such as the number of very cold days in a year or freeze-thaw cycles. There are your regular temperature variables, such as mean, maximum, and minimum temperature. And if you click on the triangle, you'll notice that we offer it from an annual perspective, seasonal perspective, and a monthly perspective. There are precipitation-related variables, such as heavy precipitation days or wet and dry days. And then there's also your annual, seasonal, and monthly precipitation. Finally, there are variables related to agriculture, such as the frost-free season or corn heat units or growing degree days. Next, you'll want to select what time period you're interested in. If you select the information icon next to the time period, a pop-up will appear, which will explain a bit more about the different time periods. We've chosen 3 30-year time periods for you to choose from. There's the recent past, which is 1976 to 2005, and this represents the baseline period before the climate models take into consideration the different carbon emission scenarios. There's the immediate future, which is 2021 to 2050, and then there is the near future, which is 2051 to 2080. And again, by selecting a different time period, the map will change. If you select a future time period, you can also choose how much, what carbon emission scenario you want the models to display. Again, by clicking on the information button, it'll give you more information about what the options are. So there's 2 different emission scenarios. There is more climate change, or the high carbon scenario, which is RCP 8.5, or there's less climate change, or the low carbon scenario, which is RCP 4.5. You'll also notice that there are these play buttons on the map. These represent all of the short documentaries that have been taken all across Canada. And by clicking on a video, a movie screen will pop up and allow you to watch local stories about climate change. On the left-hand side, there are also more options that can adjust the way you view the map. There's where you can change the size of the grid square that you want to see the climate data on, either large, small, or from a provincial or a territory perspective. You can also change the type of map you're looking at. Right now, we are looking at the average value for 2021 to 2050, but you can also look at how much those values have changed from the baseline period, also known as a delta map. You can also change what sort of place names are visible on the map. Right now, we're selecting cities and municipalities, but there are also over 600 First Nation community place names on the map, as well as Inuit communities and Métis conservation projects, which when clicked on give you more information about a specific conservation project that is happening in the Métis homeland. Finally, there are other settings that allow you to adjust different map layers, such as adding rivers or watersheds to the map or removing the video markers. If you're ever wondering about what the map is showing or want more information, there is a map information button on the top left that when you click provides you information about the emission scenario, time period, as well as the climate variable. There are also helpful buttons on the top right that can provide you more information about how to use the map. Finally, on the sidebar, if you scroll through the sidebar, there are other neat things that you can discover, such as the time series of the full 150 years from 1950 to 2095 of showing all the models, the ensemble mean, as well as historic values. There's more information about the mean value you are seeing. It gives you the 10th percentile and 90th percentile of the model ensemble range. There are downloads as well, such as the climate summary report. And these are available for every grid square, every region, every place name. There are also downloads of the map, the time series, and the time series graph, as well as links to the data and methodology that we used, if you want to find out more information about that. Finally, there's a link to explore more detailed climate data about the location you selected. So by clicking on the link, it takes you to our local data page, where you can explore the climate variable and all of the climate variables through 4 different types of graphs: a time series graph, a frequency plot graph, scatter plot, and a climate graph. And these are available for all locations on the map and all across Canada. And for now, I will go back to the PowerPoint. So I mentioned RCPs and emission scenarios in the walkthrough of the Atlas, and I just wanted to touch on it a bit more before I hand it back to Stephen. So emission scenarios are important because they help illustrate a range of potential futures based on a number of different factors, such as varying amounts of greenhouse gases, radiative forcings, or projected rates of warming. And in this way, they are really useful for the IPCC and climate modelers alike to talk about the future. Next slide, please, Stephen. So the scenarios that are presented and used in the Atlas are called representative concentration pathways, or RCPs. And they are based on radiative forcing at the end of the century, which is the combined effect of greenhouse gases, aerosols, and other factors that influence the climate. So the Atlas uses 2 RCPs, RCP 8.5 and RCP 4.5, but there are a range of RCPs, such as RCP 2.6 and RCP 6.0. And by the end of the century, these RCPs represent a different range of global surface warming. And so we have chosen the high emissions projection and a medium projection to give you a range to show different levels of warming through the end of the century. And it's important, in my mind, to look at it from even if RCP 8.5 won't occur, We need to prepare for the worst and hope for the best. And at that, I'll hand it off to Stephen.
Thank you, Matt, for that comprehensive tour. And I think it's a great segue into what we're going to look at next year as well. So in applying the use of the climate atlas, we'll now look at several individual climate variables, as Matt kind of alluded to on the bottom panel there of the atlas, and see how they differ across Manitoba. I think it's a big thing to stress is that Manitoba is not a monolith. Climate change will affect different communities quite differently. So first of all, I want to make that case, and as Matt kind of stated at the end there, take a moment to make the case for using the RCP 8.5 or sort of that more climate change setting when using the atlas itself. As labeled here, these four maps look at a single variable chosen at random, the length of the hot season, under two scenarios and across two time periods. So in the immediate future, there's little divergence between the two scenarios. So if you're reading left to right, maps 1 and 3, but towards the end of the century, maps 2 and 4, the climate models deviate considerably, as we can see here, significant amounts of crimson appear in this map, as the climate models deviate considerably as the compounding impacts of slow onset climate change are revealed. So while the likelihood of experiencing climate change and global mean temperatures increase suggested by an RCP 8.5 scenario is minimal, by some research studies I've come across about 5% likely, by preparing for the worst, as Matt just said, we bet our ability to respond to whatever the future holds. So quoting Detlef Van Vuren here, in conversation with Carbon Brief, it is important to have a high-end baseline scenario to explore the idea of what could happen. In reviewing individual climate variables, we'll look at these 7 communities, emphasizing the role that latitude has on projections for each community. So starting at the north, southern basin of Hudson's Bay with Churchill, and then down to Morden near the US border. Regardless of where one is located, a few general trends emerge under RCP 8.5. We will experience hotter summer temperatures, followed by warmer, shorter winters, and lastly, an increase in precipitation variability, especially seasonally. So the first variable we're looking at here is the projected change in the mean summer temperature, And note that rather consistently, the province is projected to increase by about 4.4 degrees Celsius. We see the map color is fairly consistently orange. There's little deviation across there. And while 4.4 in many cases doesn't seem like a drastic shift, even small increases in the mean temperature results in larger shifts in the extremes, as noted by this graph from the IPCC. So as we move here to a warmer mean temperature, as we shift right with this bell curve, even a few degrees can result in more record hot temperature, but as well as significantly hotter temperatures overall, and the possibility of less cold weather. So this trend is captured with the next climate variable, which is the projected change in the mean number of hot days, or days in which the temperature doesn't get or gets to at least 30 degrees Celsius. Note that while we see sizable leaps in terms of the projected number of hot days in southern Manitoba, with the dark spots of crimson here in the south, especially in Winnipeg and Brandon, the magnitude change experienced in our northern communities is double that of our southern ones. So while Winnipeg is seeing a significant jump up to about 52.1 days and the fold increased by 3.6, Norway House is jumping to 22.2, which marks a 10-fold increase, which is significant for how that community copes with hot weather and what sort of infrastructure they have on hand to contend with that. The trend is a bit more evenly dispersed when we look at the projected change in the mean number of tropical nights, or night where the air temperature doesn't dip below 20 degrees Celsius. And similarly, we see a bit more evenly dispersed though, with those dark spots still in the south, in and around the Interlake, and then as well the east side of Lake Winnipeg, significant shift. So tropical nights put strain on at-risk and elderly populations who don't have access to air conditioning, as the body has to work extra hard to regulate core temperatures, not to mention the added strain on on buildings to cool themselves. For those living in large urban centers, this increase is exacerbated by the urban heat island effect, which can cause cities to be anywhere between 8 and 12 degrees warmer than the surrounding regions. And this is largely due to the materials that are used in building cities. Glass, concrete, asphalt, and steel all absorb heat throughout the day and then radiate outwards in the evening, as well as throughout the day as well. So that artificially inflates the temperature experienced on the ground. Another impact from warming mean temperature is this projected shift in plant hardiness zones. And I realize these maps are probably a bit difficult to distinguish those boundaries. But these three maps were developed using the US hardness zone categorization, which are based off of the average annual minimum winter temperature. And these maps use, in this case, the US hardness zone categorization, in part because the Canadian one is a bit more comprehensive. It also factors in soil moisture as well as wind direction, which we don't fully have the ability to capture right now in maps. So this shift suggests that the range of some species that are currently, say, limited to Emerson, you see here these pockets of around a 4A region in the south, will now shift as high north as Churchill by end of century if we're using this RCP 8.5 scenario. So a significant increase in terms of where these plants could propagate, but also the pests and diseases that come with that as those ranges move north. So another way of visualizing that shift is with the projected change in the mean winter temperature or the average temperature for the months of December, January, and February. Again, projected warming occurs relatively consistently throughout the province, with the north warming slightly more. So again, that gradient fairly consistent, a little bit more red around Hudson's Bay. Comparatively, though, we see slightly more warming in the winter months. We think back to the summer months of 4.4. So we see here in part Churchill 8.3, so almost double the increase as listed with the summer mean temperature. And some in the south too, Brandon and Morden 5.7, 5.8. So still small but significant. So while seemingly modest, even that small winters will be, pardon me, warmer, shorter winters we met with excitement by most of us. But bear in mind that Manitoba relies on over 2,000 kilometers of ice and winter roads to service remote communities and industries. Warmer conditions mean shorter ice roads and thawing of permafrost, which could seriously impact northern infrastructure that relies on its stability. The last temperature variable we'll look at is the projected change in the mean number of icing days, or days where the air temperature doesn't climb above 0 degrees Celsius. With fewer icing days comes more freeze-thaw cycles. This could put significant demand on public works departments as roadways degrade or using more salt, and negatively impact overwintering plants as well as infrastructures, which rely on the insulating layer of snow to maintain consistent temperatures below grade. As we stay around that freeze-thaw cycle threshold, we get ice buildup along that ground plane, which can adversely affect root structures and damage trees, especially shrubs. We see significant dieback as a result of that. So while the temperature projections consistently suggest a warming trend under both scenarios of the atlas, we should note 4.5 and 8.5 both show warming trend overall. Projected precipitation amounts exhibit far greater variability season to season, and impacts such as drought will remain a concern alongside concerns like overland flooding. Both are still at play here. So for the province, the projected change in mean annual precipitation is a 10% increase overall, and similarly, we see the stratification by latitude. So we see significantly more change occurring around Hudson's Bay and Churchill. And in the southern part of the province, kind of consistently, Dauphin, Winnipeg, Manitoba, Winnipeg, Brandon, Morden, pardon me, all around that 7% increase overall. But the thing to note, of course, is that attributing an increase in precipitation to wetter conditions is equally misleading. One anecdote from an acquaintance I know who farms near Eli, which kind of puts us right about there in that pale teal. Um, they noted that all their summer precipitation this past year in 2021 fell in just 2 days. Both those days were over 30 millimeters, but they were 61 days apart. And so the risk for producers in how do we access water and how do we act and when do we need precipitation will vary considerably, as will the response needed to how do we contend with that reality. So this variability is perhaps better captured when we look at individual months. Here we see the projected change in the mean precipitation for April, which sees significant increases across the province. And we can note these sort of darker pockets along the western edge of the province, as well as sort of in the southeast parts around like the White Shell. How and where that eventual water goes becomes a pressing issue, as stormwater management infrastructures will be expected to handle the impacts of more extreme weather events. We look to a lot of our integrated watershed management plans. One of the pressing issues is water retention and also water management in terms of peak flows and managing those when we have the massive runoff events. If we have snow on the ground in April, increase in precipitation may exacerbate the impact of that thawing and melt, which could lead to higher peak flow rates, is one of the concerns. And for contrast, here's the projected change in the mean August precipitation. If you look back to the last one, we see significant change overall, which is quite striking, with the notable decrease projected for the prairie ecozone in the southwest and even the boreal plains. We kind of dip into that slightly brown tone here throughout the southern half of the province, would suggest there a decrease in precipitation. And when we think out to those the realities and ramifications of that at the scale of the watershed, we see projected decreases as high as 18% in parts of southern Saskatchewan that are upstream in both the Assiniboine and the Souris River watersheds. And that reality could adversely impact access to potable water for producers in the summer months who are drawing from those tributaries to water. In this case, perhaps it's cattle, or in this case, perhaps grain as well. So being mindful what that means in terms of water storage, but also rethinking how and where we put the water when it does arrive is a big question moving forward. And while these are only projections under one specific scenario, the possibility that they could occur warrants careful consideration for decision makers. So I'm going to hand it off this time now to Danny to show how recent observational data compares to the RCP 4.5 and 8.5 scenario to better articulate what's already been experienced so far and how that aligns with the projections. So I'll stop sharing now, Danny.
Thank you. Well done, guys. So I'm just going to give you a brief introduction to what actually has happened at a few places, as represented by my favorite tool in climatology, the graph. If you spend any amount of time with me, you'll know that I love to show graphs. I love to make graphs. So I'm just going to give you a small taste of it here to essentially verify that what Stephen and Matt have been talking about and what I talk about all the time, climate change is here. Climate change is definitely a reality. I want to show you that that's the case. So here's let me get the bearings on these graphs. The title of the graph indicates what variable is being shown and for where. So here we have the average annual mean temperature, the average annual mean T observed at Churchill from 1932 to 2020 based upon 5 stations. That is, I went to the Churchill, the geographic location of Churchill, and I looked for all the weather stations that collected data within 50 kilometers of Churchill. And the reason I do that is because Environment Canada's weather stations over the years they come and go. They don't last forever, or they change their names, or they might change their name when they go from a manual station to an automated station, which most of the weather stations are now across Canada. And so in this case, we have only 5 weather stations within 50 kilometers of Churchill, but they do go back to 1932, and they go to 2020. And so this is the annual mean temperature. So 2020 is the last value on the graph there. And the black lines with the black dots are the temperatures, the observed temperatures at these weather stations. The data set for the data source of this is from Environment Canada originally, but most directly from something called the Global Historical Climatology Network, the daily version of it, where anybody can download on any day all of the weather station data from around the world, including almost all of Environment Canada's stations. So that's the source of this data, and it's the raw data. It hasn't been adjusted for the urban heat island effect. It hasn't been adjusted for any station changes. So I just want to acknowledge that this is the raw data, which is what I prefer to work with anyway. And the red line is the RCP 8.5 that's been discussed, and the blue line is the RCP 4.5 that's been discussed. And these are the 24 models averaged out. These are the ensemble values, and I've smoothed them. So that they're nice and smooth. And so what we see for Churchill is that there is a general trend of warming, especially over the last 50 years or so. And that is the case for much of the world and much of Canada and Manitoba included, that the bulk of the change has occurred, or a very large amount of change has occurred in the last 50 years, since 1970 or so. And we see that here. And so there's ups and downs. And of course, that's a distinguishing characteristic, as it has been said, of our climate. It's incredibly variable. You're not going to find very many places around the world that have as variable a climate as we do. One year can be very different from the next. One season can be very different from the next, because there's all kinds of forcings. And on top of that is the forcing related to greenhouse gases that are now very much changing our climate. And so we do see that we don't, from an annual point of view, we don't see the kind of temperatures in Churchill that we used to in the past. I've chosen not to put on linear regression lines and statistical techniques here, but there are very strong statistical trends across Manitoba in temperature variables in particular. And here's the winter temperatures in Churchill based upon those, again, same 5 stations. And you can see that some winters are really warm and some winters are really cold. But on average, the winters now are warmer than they were in the not too distant past, and are projected to become much warmer, whether they be under the 4.5, the lower carbon scenario, or under the higher carbon scenario. And remember, as you look, if you look forward in time, which we encourage you to do, of course, you have to superimpose this variability on those lines. And so it's not just going to be that temperature or that temperature that is exactly along the line. It's going to be all over the place as well. So an enormous amount of variability in the future as well as in the present and the past. And here's the temperatures for Morden. Here we have 20 stations, so that it gets a little bit messier, the 50-kilometer station set. And these go back to 1905. And you can see in particular in the last 50 years or so, there is a general trend of a warming in the annual mean temperature observed in Morden. And if I go to Winnipeg, we see the same kind of thing. And our data goes back to 1873 for the annual mean temperature. We started to collect weather data in Winnipeg, not too far from my office here at the University of Winnipeg in 1872. And then in 1938, we switched to the airport. And then there are other stations within 50 kilometers of Winnipeg, of course. But generally, they all say the same, they all show the same thing. And that is, it used to be really cold in Winnipeg, and now not so much from an annual point of view and otherwise. And so there's if we're going to follow the 4.5, or especially if we follow the 8.5, we're going to have much warmer temperatures on average for the year and on a seasonal basis as well. Here's the winter temperatures in Winnipeg. And again, these go back to 1873, the winter of 1873, which is 1872-73. And of course, winters more so than any other season are incredibly variable. Lots of ups and downs. Notice this one over here in the late 1870s. That is not a mistake. That was an incredibly warm winter, very out of character for the really cold winters that occurred at the end of the 1800s. This was a very, very strong El Nino event. And an El Nino event, of course, is when the Pacific Ocean is warmer than normal. The world tends to be warmer than normal. The jet stream gets disturbed, and warm air generally flows into Western Canada during these El Nino winters, and it sure did in that particular winter. And we get a lot of these really warm winters are El Nino winters, but we haven't had a super duper El Nino like that, thank goodness, because it would be off the chart, the temperatures. We do still get cold winters, and we're likely, according to Environment Canada, to get a cold winter this year because it's a La Nina winter when the Pacific Ocean is colder than normal. This dot right here is this really cold dot right there. That's 2014, the winter of 2013-14. That was the year that in Winnipeg, we had lots of frozen pipes, lots of infrastructure damage, a bitterly cold winter. And that can still happen even in a warming world. But on average, we're seeing winters that are shorter and warmer, including the winter of last year, the winter of 2020-2021. We had very warm temperatures on average across Western Canada. Other winters have been warmer, that's for sure, and generally those tend to be El Nino winters. Last year was not an El Nino winter. It wasn't warm because of El Nino. There was a La Nina going on last winter as well. And so superimpose that amount of variability and the occasional really warm El Nino, and you see an enormous amount of variability continuing to come our way in the wintertime, but on average, much warmer. And I assure you that this is not the urban heat island effect. This trend here is not because of the concrete jungle of Winnipeg and the furnaces and the absorption and retention of heat by our structures. This signal is found across all of Canada, all of Manitoba, at Morden, at Dauphin, at Emerson, all the stations that have recorded it. And then, of course, we just came through a rather warm summer, as has been pointed out. Here's the average summer mean temperatures in Winnipeg, 1873 to 2021. And you can see that there is a trend in the summer temperatures. Those black dots right there, those are the summer temperatures this past year. The one at the top there, that's the Forks, which is a little bit warmer than the airport, but the airport was very warm as well. And we haven't had in quite a long time some of the cool summers that we had in the 1980s and 1990s. We are always going to get lots of variability, that's for sure. But undoubtedly, we're going to see the averages go up and up and up. And then as Stephen pointed out, some of the summer months, July and August in particular, are expected to on average get drier, And so when you superimpose, as happened this year, dryness with heat, you get bad growing conditions and water shortages and all kinds of negative impacts of the sort that we don't want to happen, but we need to be prepared for. We just have to be prepared for those kinds of things. So back to you, Stephen. Thank you for that.
Thank you so much, Danny. And I will note on those maps, I realized that I identified RCP 4.5 and 8.5 wrong. They're colored the wrong. So 8.5 was the red line. The blue line was supposed to be 4.5. So I apologize. I should have caught that. I've been for a while. A couple of questions that have come in between perhaps Matt and looks like Matt is responding to one right now. One that we have from Jeff here is, can you please speak to variability as a key aspect of future weather? Imagine planning for a climate like Winnipeg, past and the future, that is sometimes more like Tulsa. And I think that we talk about what's happening in Winnipeg in terms of what we're planning for and contending with, all that's still on the table. Just when we talk about those extremes, especially on the hot end, we see that creeping up. And so conditions like Tulsa, which are probably a bit more arid and dry and a bit warmer in the summer months, are still at play, but the possibility of a cold winter is still on hand. So that range is in part growing in the near future, though over time we will see those winters be less impactful, a little bit shorter, a little bit warmer. That being said, though, minus 30 is not out of the question. We will still get that. And so from the decisions we have to make in terms of materials we choose and planning choices, we are now contending with a slightly larger range, and be mindful of what that means for materials we use, but also we're replacing infrastructures and how we're doing that are on the table.
But can I say, that's a really good question. The question is basically, it's related to whose climate are we going to have in the past and what kind of adaptation will be required. And it's definitely the case that as our climate changes all across Canada and in Manitoba here, that as we progress towards a more warmer and warmer climate, we're going to be experiencing the kind of climate that now is found in Nebraska and Oklahoma and Kansas and even Texas in the long run, if under the worst case scenario. And looking at those kinds of environments is a really good way to identify what kind of changes we might have to do in terms of our crop choices, our infrastructure choices, what kind of fabrics we use in our buildings, what kind of heating and cooling systems we might need. So that idea of looking south to see what might be coming in the future is a really good strategy. Next question.
Next, we had a couple that there's some though that Matt was great in responding to on the fly. I think Matt's responding to another one right now. Looks like one that came a bit earlier that I'll just reiterate is just in terms of the wildfire data. So the province of Manitoba Conservation and Climate has data that's available publicly up till 1914 is when we had the first registry. So we have over 100 years now of wildfire data. And this case here, I think of the worst ones, I think 3 in the last 30 years. And the worst one within that same realm, I think there's one from 1923, which is also over 1 million hectares burned. but that trend is kind of ticking upwards over time as well. You can see that growth occur. And just waiting for more questions. It's open right now, but nothing at the moment.
Well, can I just say then, I'll just pipe in, that graph that you showed that demonstrated that a small shift in the averages increases enormously, disproportionately, the expected frequency of high temperature extremes. Of course, we saw that in real life terms in this summer in British Columbia. The temperatures that were observed in Lytton and Vancouver and Victoria at the end of June and the beginning of July are just mind-boggling. And they weren't prepared for those. Almost 600 people died in British Columbia from heat stress, heat-related illnesses. And that is a mind-boggling statistic for Canada, that 600 people died from a weather event. Not a tornado, not a flood, not some kind of dramatic, intense, threatening thing, but just the pervasive stress of heat killed an enormous number of people. And one of the reasons why is because they don't have the kind of air conditioning that we have. Winnipeg has 90% of the homes in Winnipeg have air conditioning, according to Stats Canada in 2019, 80% in Manitoba as a whole. In Vancouver, 28% of the homes in 2019 had air conditioning. They just weren't able to cope with that kind of stress. This is the kind of thing we want to prevent. We don't want those kinds of surprises. We want to adapt. We want to prepare for those extremes that are undoubtedly coming in the temperature world and undoubtedly coming in the precipitation world as well.
That's a great point, Danny. One question we've got here: given the weather variability moving forward, is planning for flood and other events on a 1 in 200 year frequency sufficient? We seem to be having 1 in 200 year floods every 3 to 4 years.
Matt, do you want to tackle that?
Sorry, I'm just rereading the questions. More questions are coming in.
Okay.
Yeah, I think we need to start adjusting our timeline for what sort of events we plan for. As Stephen mentioned earlier, the normals, or what we have once considered normals, are changing. And so do the frequency and intensity of these events. And so it's tough to say exactly what is the defining, 1 in X year to plan for, but we need to be aware that we need to start planning for things that are happening more frequently and more intensely. I'm not sure if any, Stephen or Danny, you want to add to that?
That's exactly right. We need to prepare for shorter return periods for extreme events. There's going to be shorter distance, time-wise, if you will, on average between the extreme events. They're going to occur more often, especially for the short duration precipitation events, those intense rainfalls that are associated with, the high temperatures of the summertime. As your friends in Eli said, they got a good amount of rain, but it came in an ineffective way. It came down in gushes, essentially. That's the kind of thing we need to prepare for and prepare our infrastructure for.
I think to their credit, one thing they did this past year, though, is they actually extended a large dugout to capture a lot of that water, to keep more water on site. It was an advance they did. And I'm going to go there and visit it soon, which I'm very excited about, to go see it in person. Another one that came in here: how does the projected maps compare to those heat events in BC? Can they be predicted in the short term?
Yeah, well, the statistics of these extreme events is problematic. They're difficult to forecast in the short term, but you need to expect them in the long term. That's not a satisfying answer for a lot of people, of course, because you want to know when they're going to come. But the lesson learned here is that they are going to come. And for that, those extreme events, both the heat and the precipitation events in British Columbia, it's evident that climate change exacerbated them. That is, extreme events of these sorts are normal in a way in all climates, including ours. But climate change ups the game. Climate change makes them much more likely. And we shouldn't have to rely upon the terrible experiences of British Columbia this summer and this fall to wake up and get ready for them, because one of these days is going to be our turn, whether it be with a a really long drought or really intense precipitation events or really high temperatures of the sort that devastated the West Coast this year. We need to prepare for these things. It's the prudent thing to do.
I think prudence is a great word to kind of latch onto. That's a great way of putting that, Danny. The IPCC AR6 data sets are now out, and they are no longer using RCPs. Do you have a timeline for when AR6 data will be included in the Atlas map outputs? Very timely question.
Go, Matt.
Great question. We are currently working on that data set to start incorporating it into the Atlas. An exact timeline we don't have, but we're hoping to get it out early sometime next year.
Fantastic. It looks like agriculture and infrastructure in the north are areas that will require special attention with more fundamental shifts or changes. Is there focused research and work on adaptation? Broad question, and in part, I don't know if I know the answer offhand. I know in terms of Canadian Standard Council for, in this case, for like codes for building requirements, they are updating those in real time to reflect the changes that are projected for the north largely. So in terms of infrastructure, we do see updates being made. At that point, though, it is under the purview of individual municipalities to adopt those standards as sort of the guiding metric moving forward or at the provincial level. And so those documents are currently being ratified and are being produced.
Change. The farming community in general deal with enormous amounts of variability and volatility in their world, including in the weather world. And I'm confident the ag world is working on it. I know they're concerned about it. Keystone agricultural producers are taking climate change very seriously. I'll be speaking at their annual conference in January. And I think that's just indicative of what's happening in the ag world. Let's just hope that the adaptation strategies and the incentives and help to move those along comes on as fast as it needs to.
Fantastic. And the last question is kind of in the same vein. What are your thoughts on the impacts of climate change scenarios you described on livestock production in Manitoba? I think the same thing in the years like we had this past year with drought, we saw having to import a lot more grain, and for some producers having to sell off heads of cattle and steer to make up that shortfall and not be able to feed them. And I think that's a concern in drought years especially, is how do we manage and keep the health of these livestock in check? And I think that's, again, I think there is work being done in that field. As to what I know myself, I can't speak to that a lot, but I think Keystone producers are looking at that. I know efforts with ducks as well for more wetland restoration and water retention on land is one such effort at the watershed level that is being undertaken. I think Carrot River is a great example of some really meaningful work, as has Cooks and Devil's Creek in sort of southeastern Manitoba has done some really wonderful work in mapping and planning for more retention of water to ensure there is access to the needed amounts to maintain livestock going forward. Well, no questions now. We're coming to the top of the hour, so I think we might call it there. Thank you everyone for joining us today. This recording will be made available probably about a week's time on the MCRT project website, and please reference that for future courses. The planning sector is delivering 2 more workshops in the new year, and there's a bunch of other great resources on there as well. So thank you all so much, and thank you, Matt and Danny, for joining me once again.
Well done, Stephen. Thank you.
Thanks,
everybody.